So why do we care about these induced magnetic fields? Well, that's pretty much how everything cool happens. It's how generators happen, which we'll talk about next time, but it also has tons of applications that we can basically induce a current. We can create a current without touching anything. We just need a magnetic field that's changing somehow, really a magnetic flux that's changing. So this concept is used in roller coaster brakes, that as the brakes will move through the magnetic field, it creates this induced current, which actually slows it down. So I have this gizmo that we can bring to class, so then you can basically wave a piece of metal through a very strong magnet and find that it does resist that change. We can also use it to levitate things, to make things not fall nearly as quickly. So here the outside coil is creating a magnetic field. That magnetic field is inducing a current in our little agate here and causing it to heat up. And this is exactly how an induction cooktop works, is that it induces a current in the cookware, which then gets it hot, and that's how you cook, and the stovetop remains quite cool. We can also do fun tricks like this, and this can also bring to class where you can drop a magnet through a non-magnetic material like aluminum or copper and find that it falls quite slowly. Then we also see this in brakes. So your brakes on your car, you have brake pads, and those wear them out. Whereas exercise equipment, you don't want to have a whole bunch of wear parts, so you can adjust the amount of resistance in the equipment by adjusting what they call the tension. But really what you're doing is adjusting the distance to between a magnet and a plate of metal. And this creates a force so that you can basically have a harder time pedaling and get better exercise. So it uses basically an eddy current brake to introduce some friction into the system. We also use this whenever you're using microphones. This is what is in an electric guitar. Is basically the string is metal, it has metal on it, and is able to be magnetized, and then the microphone picks up the movement of that metal in the coil and the magnet there. So as the wire moves back and forth, when it's plucked, the magnet changes the flux in the magnetic field and induces a current in the microphone circuit. We can also use these for apnea monitors. Basically, you can wrap a metal coil, obviously protected, around the infant, and as the area changes, as the infant breathes in and out, then it will create a change in the magnetic flux using the Earth's own magnetic field, and we are able to pick up that that is changing, and if that is not changing and the rate that we think it should be for the infant, and the infant stops breathing, we can pick that up on the monitor and know instantaneously that there's an issue. We also see this almost every day. They're getting away from these tiny sensors, but these induction sensors are in the road. You probably have seen them at traffic lights, as they have a cutoff out in the road, and they put basically a coil of wire there that's attracted to the light. When a big metal car sits on top of one of those sensors, it creates a change in the magnetic field. The sensor is able to pick up that change in magnetic field and send the signal to the light. We also see this in airports when we're going through the metal detectors, or if you have a metal detector wand that you take to the beach to find treasure. This is also how that works. What I'd have you do next for your question is actually watch a demonstration from a different instructor, and my question for you on this for this purpose is a little bit different than what hers is going to be. She wants a complete explanation, but I'm going to simply ask you that she has a full ring and a split ring. Why does the split ring not react to the magnet? So your choices are: there are no eddy currents. Eddy currents are formed perpendicular to the magnet, or the split causes retroactive current. So watch and observe and see if you can figure out what's going on.
Now, this exercise is simply one where you observe and explain. And what you're going to be seeing here involves Lenz's law. So the apparatus first. I have this aluminium set of a bar and two rings. Aluminium because it's not ferromagnetic, so it's not attracted to this large magnet I've got. they're on a metal, they're on the bar, and this whole bar is free to rotate. And you can see that one of the aluminium rings is a complete ring, but the other one has got a cut in it, so that's not a complete circle. So let's start with looking at how the complete circle behaves as a magnet approaches. This is a strong magnet, and this is the North Pole. So I want you to look at what the ring does as I move the magnet. So there are two different things happening here. As I move the magnet towards it, the ring retreats. But as I move the magnet away, the ring tries to follow it. If I kept on moving the magnet, in fact, the ring would retreat further, but I don't want to actually bump the thing and make it move because of that. So, let's now have a look at what the broken ring does. And now, when the magnet approaches, or when I move it away, we're getting no response from this at all. It's not moving, except when I bump it. It isn't moving in the slightest. So, I'd like you to try to explain this one in terms of Lenz's law, induced current, and therefore induced magnetic field, and how that is making the ring respond to this magnet.
Now my question for you, though, is why does the split ring not respond? And so the answers are given here. And so basically it doesn't respond because it cannot create a magnetic field inside the ring, because it cannot create a current all the way around the ring, so there's really not much of a current formed. Now there can be little teeny tiny currents inside the material, creating little magnetic fields in the material, but that is not big enough to respond to the magnet. So basically there are no or very little eddy currents formed in that split ring because it cannot go all the way around. It's an open circuit.
Now, this exercise is simply one where